All right. I will begin. I will begin with a word of prayer. I will attempt anyway. Heavenly Father, we thank you for this day. Again, I thank you for this class and for the break that's about to start. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, I have something to show you guys today, if I can find it. So, I just want to run through these notes with you because I think they're kind of interesting. So we talked about this before, but this is just kind of a review. How much energy does it take to assemble a collection of point charges, right? We talked about it. The first charge you can just put there. It doesn't take anything because it's not being opposed by the electric fields of any other charges, right? So the first charge, put it in place at Q1 at R1, zero work, right? But to put the second charge into place, we end up having to multiply. Basically, the work we have to do is the voltage times the voltage due to the first charge, where the second charge is, times the second charge. This gives us the potential energy that is built up by moving Q2 a distance R12 from Q1. Now, this of course assumes that we're moving the charge from very far away, and also that we're just we're putting voltage. We're using the voltage zero at infinity thing to set up the voltage functions. But so here's a picture of what's going on with two charges. You just got this R12, right? Okay, great. Then you add a third charge. Then what happens? Well, then you have to do work. I mean, how much additional work does it take to add the third charge? Well, then you have to work against the electric fields from the first and the second charges, which are already there, right? So basically, you've got the voltage due to this distance, the voltage due to that distance. And so this gives us the voltage at R3 due to Q1 and Q2. And we multiply by Q3. That gives us the energy needed to add that third charge, right? So at this point, the sum of W2 and the sum of W3, that would be the total energy to assemble these three charges in that configuration. So next, we add a fourth charge. All right, so we're just basically, I'm just going to do 4 steps. It'll be enough for us to see the pattern, is the point. So we add the fourth charge, and then, I didn't draw the picture, but we'd have the voltage due to the first one, the second one, and the third one, all of that times the fourth charge. And this, again, is the voltage, the potential energy per unit charge due to charge 1, charge 2, charge 3 at the position where our Q4 is. So it's the same pattern every time here, if you think through it. And so then what we do next is just to generalize that a bit. Well, we're not quite to the generalization. Next, we just add them all together, right? So what's the total work needed to bring 4 charges into place? Well, it's this plus this plus this plus this plus this plus that, adding together everything we did, right? Now, I did this for a very uninspired numerical example in class, right? And we didn't really get any kind of insight as to the pattern that was happening there because I used numbers, right? But if we stick with a little bit of abstraction here, you can start to see the pattern, right? It's just like 1 less than 2, 1 less than 3, 2 less than 3, 1 less than 4, 2 less than 4, 3 less than 4. We can arrange the terms like this, right? So it's got all possible pairs where you have one less than the other, right? So if you extrapolate this pattern, as is done in David Griffith's excellent Introduction to Electrodynamics, 3rd edition, where I stole this argument from, you can see that you have the same pattern for n charges. You get 1 over 4 pi epsilon naught, the sum I equals 1 to n, of all the j that are greater than I. So you have I less than j pairings here like that, right? Do you guys agree? I mean, I'm kind of begging a question. I did it for 4. I'm saying, oh, if it's true for 4, it must be true for n. But usually engineers are content with proofs by 3. This is 1 more than that. So you guys should be 30% more approving of this proof than usual. Something like that. That's a joke. Okay. I mean, maybe it wasn't a joke. I mean, It's debatable. Anyway, it's an argument. 30% of 0 is still 0. Ooh, you hurt me with that. I'll allow it. I walked into it. So generically speaking, that's what we have. But then we can pull a fast one here and divide by 2. But when I do that, I double the number of terms over here. So I'm not imposing I less than j. Now I'm allowing I greater than j or I less than j. So it's got everything except for I equal to j. So I'm doubling the number of terms there. That's an acceptable sleight of hand, in part because the Rij is equal to Rji, right? Because the distance from I to j and the distance from j to I position, it's the same distance, right? That's a property of distance and displacement. The magnitude is invariant from starting to ending point. Anyway, so I can rewrite it like that. And then what I do is I pull the sum over I out. Notice that this has no j dependence, so you can pull the I out like so. I know it always sounds kind of violent when you start talking about pulling i's out, but there it is. Let's see here. And look what we have. We have 1/2 the sum I equals 1 to n of qi. And this right here, what is this? This is the voltage at the ith position due to all of the other charges except for the ith one. So we're just adding the Coulomb voltage, the Coulomb potentials for all of the charges except for I, and evaluating it at r sub I. So I would point out that's kind of neat because this gives you like a formula that you could use to calculate the voltage, calculate the work it takes to assemble a system of charges without doing that step by step. Oh, I'm doing this much to add the next one thing and going through step by step by step. I could just say, oh no, it's just this, and I could just write down what those are. Now, it's the same. It's going to be the same formula, and maybe it's easier to remember the step by step process I did in class. But I'm just pointing out that there's, you could use this for other problems, if nothing else. Now, next step. Instead of thinking about n charges, think about infinitely many. So pass to the continuum, all right? Think about the number of charges going to infinity. Then this summation rather, over n is going to become an integration. And so that's what we'll do next. So if we do that, instead of having, so the summation over qi, I should make them both visible, my bad. I want you to see what I'm doing here, okay? So this is the formula for work for n of them, to assemble n of them. I'm saying that this is what we get if we pass to the continuum. So the 1/2 is the same. Qi becomes dq. V is the voltage where this dq is. All right? It's the voltage where the dq is. And then how do you actually do such an integral? Well, you trade the charge for the density times the volume. See, rho is dq d tau. And so what this is the density times the voltage integrated over the volume where we find the charge. And that should give me that should be the work that's required to assemble a continuous distribution of charge. Now, I don't know if you guys remember or not, I derived a formula for the energy in the electric field, right? We looked at a capacitor, and we made a simple argument that we derived epsilon naught over 2 E squared as being the energy per unit volume due to the electric field. What I'm in the midst of here is trying to show you why we can derive that in general. So we're halfway there. We've got this formula for the work. Oh, come on. This formula for the work that's needed to assemble the charge. Now, this should be integrated over an appropriate region, like where all the charge is, all right? But you notice that the divergence of the electric field is the charge density divided by epsilon naught. Remember, this is the differential form of Gauss's law. So I can solve that for the charge density and replace a rho with the divergence of the electric field, like so. Plug that in here, right? You're like, well, okay, how does that help? Well, let's see how. Now, you guys are in Calculus 3, so we're about to do some Calculus 3. So suppose B is the region in which the charge density is non-zero, and the boundary of B we denote partial B as per usual. All right. I want to show you that there's a formula, a product rule for what's called the divergence of a vector field, something you'll learn in about a month in your course. At the end of the course, in chapter 17, 18, I don't know, whatever the last chapter, the vector calculus chapter, you learn about the divergence of a vector field. And the divergence of a vector field is simply the sum of the partial derivatives of each, like it's the x derivative of the x component plus the y derivative of the y component plus the z derivative of the z component. That's the divergence. So here's a formula for it. I equals 1 to 3 partial xi of the ith component. Well, the ith component of a scalar function times a vector field is just the scalar function times the ith component of the vector field. But then, product rule, it gives me these two terms, and then you just have to tilt your head and squint and see what this is. Well, this is x with x, y with y, z with z. This is the dot product of the gradient of f and the vector field g. And this is just f times the divergence of g. All right? So this is a product rule for the divergence, and I can apply that in the case that the f is equal to the voltage, which is a scalar field, right? Scalar function, and the g is the electric field. I'm going to apply this a vector identity in that context. And if I do that, then I get this lovely identity right here, that the divergence of the electric field times the voltage is in fact the divergence of the voltage times the electric field minus the gradient of the voltage dotted with the electric field. But what's minus the gradient of the voltage? You guys have potential, you know this, right? The test is when? Next Wednesday. Before then, know what I'm saying from the bottom of your heart. Understand that the electric field is minus the gradient of the voltage function. This is something I want you guys to know. So the gradient of the voltage times that minus is the electric field. This is something you guys should all know. Now the electric field dot the electric field, that's the magnitude squared, right? That's E squared. And then there's this term over here, which is a little kind of funky, but we'll deal with it. Well, I'll deal with it the same way Griffith deals with it, which is basically to ignore it. But so here it is. I trade my previous integral for the integral of the divergence of the voltage times the electric field plus the electric field squared. And then you can use what's called the divergence theorem. There's two things going on. The one is just that the integral of a sum is the sum of the integrals. That's nothing especially interesting. I mean, here, going from here to there. This right here, though, is the divergence theorem. You can trade a volume integral for a surface integral. Remember, we looked at this before in the previous homework. It made your homework easier. You're like, yay, thank you. Maybe some of you accepted it. Anyway, so like a lot of you. And so we have this integral over the boundary of B, the surface integral of the voltage times the electric field. Like, that's a really weird integral. I believe there are abstract reasons that you could argue that's zero in general. I haven't worked through it. I haven't, fussed with it too much. Another argument we could obviously make is if the boundary, if this B we're looking at is like really large, then we can assume the voltage is what? If the charge distribution is finite and it's closed in, right? We can set it so that the voltage goes to zero far away, right? So then this would just be zero and that drops away. So for hand wavy reasons, this goes away and we're just left with this right here, which is what we derived from the capacitor argument. So what we see then is that the work that it takes to assemble a continuous distribution of charge is simply the integral of 1/2 epsilon naught the electric field that the charge builds up as a consequence of its geometric configuration. And so again, 1/2 epsilon naught E squared is the energy per unit volume of the electric field. So I think I have shown you convincingly why we don't do this in this class. Right? Because I asked Dr. Boudera, I was like, how do you present the energy density of the electric field? And he's like, well, I look at the capacitor. I'm like, lame. I guess it's not lame. It's just this is too hard for this class. I don't know. Is it too hard? I don't know. It's meh. Usually it's too hard, but I'll say that much. Anyway, so that's that. Do you guys have any questions? So I'm just, the whole point of this was just to derive the energy in the electric field per unit volume is 1/2 epsilon naught E squared. So if I was to ask you a question about like how much energy is stored in the electric field, you'd want to integrate the electric field over that volume, whatever that looked like, right? And the thing we know best is what's the energy stored in a capacitor? That one's easy, right? 1/2 QV, or 1/2 Q squared over C, or 1/2 CV squared. Did I get those right? I hope I got those right. Once upon a time, I knew those with more certainty. So yeah. So do you guys have any questions about anything? Because obviously there's no problem session this Friday. And I think next class you guys turn in your next homework. We'll talk about the homework solution, and then the class after that is Judgment Day, right? So if there are any questions that remain about the material, now would be the time to ask, you know? Let's see here. Well, if you guys don't have a question, I will try to find a problem to work then. Let's see here. What was that? Let's see if we can figure this one out. I'm just going to draw the circuit up here and then we'll ask some questions about it. So we've got 2 ohms. We've got a node here at A. We've got another 2 ohms over here. We've got a node here at B. Then they put a 1 ohm up here just to mess with us. And, ooh, yowzers. 12 volts, like that. And then there is another 1 ohm over here. And I'm getting really tired of writing ohm. I'm going to start using R instead. R. And then 10 volt supply right there. And then 3R right here. And then, man, think they got enough resistors in this circuit? 2R down here. And 3 power supplies. Man, this is really quite an ordeal. I hope we can solve this. Let's see here. R. All right, so this guy is 8 volts. And this guy is 10 volts up here. So this is figure 2657 in the textbook. And we are asked the question, find the potential of point A with respect to point B for part A. And then part B, if points A and B are connected by a wire with negligible resistance, find the current in the 8-volt battery. All right, so there's 2 questions. Part A is figure out the voltage between A and B, right? So I'll put that up here. So part A is find VAB, right? And then part B is connect A and B with wire, and then find, what did they say for us to find? The current in the 8-volt battery. Well, that's funny. So then they're like, find the current. I was expecting us then to ask me to find the current, you know, where A and B were, but no. They instead ask to find the current down here. Let me call that I guess I'll call it I1 since it's what we're interested in for part B. All right, so let me put some plus minuses in here just to keep myself honest. This is minus plus, minus plus, and I think the book has these too. I don't always give those in the problem statement. They're to be understood, right? The longer thing is where the positive is, the shorter ones where the negative. That's the meaning of the symbol. So guys, any ideas? All right, so before we connect A and B, question, does any of this matter? I mean, let me say it a different way. Before we connect A and B, can there be current flowing here? No, right? So there's no current flowing here, which means that going from here to here, what's the voltage? Incorrect. There's still a voltage source here. So the voltage going from here to here is 10 volts. It's just that there's no additional voltage drops or gains from current flowing there. Yeah? So because there's no current flowing in the middle branch, we can use the equivalent, basically just replace this with an equivalent circuit, I think is the fastest way to solve this problem. See, so for part A, excuse me, I'm gonna, well, I guess I did this, didn't I? So, permission to, I just, for some reason, that's more natural to me. I'm so sorry, guys, but that way. So if I do that, I've got what? I've got 8 volts minus I1R minus I1 times 2R minus I1 times, can I just not do that? Minus I1 times what? 1, 2, see, 1 plus 2 is 3, 5, 6, 7, 9. Right? But what else happens? And to be clear, those are drops, right? Is this 12 volts also it's also a drop, right? So minus 12 volts. And I think that's everything if we go around the loop, right? That's everything. That's everything. And so that would suggest to me that, well, among other things, my original direction was correct, haha. So I get what? I get, yowzers. Minus 9I1R equals to apparently 4 volts. So I1 is equal to minus 4 volts divided by 9R. What was R equal to? For this problem, I never told you guys this yet, but R was equal to 1 ohm. So yeah, I guess I should have told you that before I used it, huh? My bad. Can you forgive me? No? You guys are like elephants, you remember? Kill me later. I don't know why YouTube knows this, but it knows that I needed to see elephants killing things mercilessly. It's really, I tell you, when an elephant decides to kill a crocodile, it's really something to behold. See, it's a beautiful thing. Like, YouTube gives you a 2-minute video. That would have been like an hour-long, like, thing on TV. And they would have just dragged it out. And finally, the last 3 minutes of the show, you'd finally see what you're waiting for. But YouTube, it's just there. Yay. Assuming it's not important to your way of life and like information that you should actually have and are shielded with, because various various government and technological companies decide that they know better than you do on how to live your life. Ignoring that, of course, YouTube's great. 4 divided by 9. Let's see here. Minus 0.44. I get minus 0.44 amps, I think. Now, if I'm right, which I'm a little bit nervous, I did make the stupid mistake of solving an odd problem, which you guys can check me on. We're working number 2657 at the moment. And if I've already worked this in the problem session, I'm sorry. Did I? Okay, good. Whew. All right. It didn't feel familiar, so. So now that we figured out the current, what can we do with that? We can figure out VA. We can figure out voltage drops, right? So that means, goodness gracious. So that means that the, sorry, I'll get it eventually. VA. Yeah, I hope when I come back from break this is gone. So VA should be equal to what? 8 volts? What? Minus I1R. Oh, I'm sorry. I guess I should declare my intentions here. I've decided this is ground. Okay? If that's all right. I decided I'm going to make that where 0 is. So I've got 8 volts here. I'm losing I1R, but I'm actually gaining because I1's negative rather. And then, well, and then minus I1 times 2R. At that point, I'm at my target destination. All right, so that should be VA. And we can work it out. Relative to the ground, we've got what? 8 volts minus 3 times 0.44. And I'm going to add another 4. It goes on forever. There, 4 fours. That seems right. That just feels right. And an amp, that's volts, because I got amps and ohms involved here. Let's see here. And what do I got? Times 3. I believe we've got, 6.66666, we'll do 6.667, there we go, 6.667 volts is VA. I guess I shouldn't have put ground there. I didn't realize it was such an evil choice, but I'm sorry, I'm an idiot. What's VB? 10? But it's not. See, I mean, 10 volts from here, right? So it should be 2R. How does I1 go through here? I1 goes this way, right? So, yeah.
Didn't we say that I1 was negative, but when you plugged it in, it was positive?
Thank you. Thank you. Yes, there's supposed to be plus. Oh, good. Yay. Haha. Take that, Satan. Let's see here. 8 plus 3 times 0.444. 9.3332. There we go. Thank you. Thank you. I appreciate that comment. So then what? We've got 2. So this you notice the difference here. I was starting at this point and going plus minus. Now I'm starting at this point and I'm going minus plus. So I get 2R times I1. And then notice it's again minus plus, so plus 10 volts. As I've explained, through here, there's no voltage drop or gain on the 3R and the R, so we just must be 10 volts from here to there. And so what's this? 10 volts minus 2 times 0.444444. All right, this is volts because it's a amp times ohms. And great, so 10 minus 2 times 0.444444. All right, so I get like, 9.1112. I don't know. I get 9.1111. I'm a little bit sketchy on the digits here. So then what's VB minus VA? I get minus 0.2222. Whoa. Oh, yep. Now I'm scared to look in the back. I'm always scared. 26. 2657. Whew. Plus 0.22. Have I misread the problem? What is the potential of a point A with respect to a point B? That's A minus B. Yeah, so plus that because I misread the problem. The problem asked for VA minus VB if you read it. It said the voltage at A with respect to VB. All right. So another way to interpret this problem is you could just put this as ground and work it out from that. But I just don't think, I don't know. This is what's most natural to me for part A. All right. So plus 0.2222 volts was the answer. Hooray, hooray. All right. Now what happens for part B? Let's work that out. Once we connect the wire there, everything I've written out here is pretty much trash. Right? Because the assumption that no current's flowing is gone, which means that I1 is no longer what it was. Right? Which is good news because I need room to work. So it comforts me that everything I can have up here I can erase because it's no longer true. So, hooray. Let us connect a wire right here, like that. And let's see if we can solve this thing. What? All right. Nice try, Mr. Juice. Wait a minute. Did you guys come up here and break this when I wasn't watching? If so, well played. It snapped off inside the thing. Oh man, that's a bummer. I don't know if I can get it to... This ends with me spraying myself in the face, I think. Nope. Well. One. Yep. Sorry, Kirk. You may be sitting. You ever seen Gallagher? No. Oops. Now I don't know what to do. Ah. Oh man. That is. That's annoying. All right. All right, so now we have, this I1 is fine, right? I1 is like that. But now we need to define other currents, yeah? So we can define I2 up here. And so I2 goes here. I2 goes also here, right? So I got I2 go here, I1 goes here. I'll make I3 go this way, right? So if you look at this node right here, can you tell me how I1, I2, and I3 are related? Looks like I2 should be equal to what? I1 plus I3, I think, right? We agree? All right, and now we need to use Kirchhoff's voltage laws to figure out what else is going on in here. So I'll do the lower loop to start with. I've got 8 volts, all right, minus I1R minus I1 times 2R, right? And just to, let me illustrate what I'm doing the lower loop. So I'm going to go like this, all right? So I'm starting here, that drop. Now I'm going over here. Notice that this is plus minus, and this is plus minus with the current 3 going that way, right? So I'm going this way, so this is actually plus I3 R. And then let's see here, minus 10 volts, minus the 10 volts, and then plus I3 times 3R. Right, and now I'm to here. Now I'm back into the current 1, so I do minus, yeah, plus minus. So minus I1 times 2R, and I think I'm finally back where I started. So that's equal to 0. I think we can clean that up a bit, right? Yeah? What we got? So I'm going to go ahead and just divide everything by R. What are my voltages here? I got one here. I've got one here. Any other voltage? That's it, right? So this gives me, if I bring those to the other side, I get 2 volts. How many I1s do I got? Minus 1, minus 2, minus 3, minus 5. I1. I'm going to divide by R over here, so I don't have to write R all the time. So minus 5 I1. How many I3s do I got? 4 plus 4 I3. I think that's it for that equation. You guys want to double check me? All right. Now let us do the loop up here. Where do you guys want to start? No preference? I'm starting here. All right, so so let's see here. So if I say that that's 12 volts, I got 12 volts, and then plus I2R. So you notice the minus plus and the minus plus is in the same way. And then plus I2 times 2R. here. Now I'm at point A. Oh, again, a plus I3R and minus 10 volts, and then plus I3 times 3R, and then let's see here. Okay, so then plus I2 times R. And I think I finally got back where I started, so equal to 0. All right, so I'm going to bring all the voltages to the other side. And I think I get minus 2 volts over the resistance this time. I'm bringing them to the other side, but I'm writing them on this side. I know I'm sorry if it's confusing. And then I'm just keeping everything here. So I got, how many I2s do I got? 1, 3, 4. So 4 I2. How many I3s do I got? Also 4. 1 here, 4, okay, plus 4. Is there anything else? All right. You get back. Well, yeah. I'm gonna be lazy. Leave it. All right. So, of course, we could set this as equal to minus 2 amps, and this one, of course, is equal to 2 amps. And if you want, we can just omit the amps and just work an implicit unit of amps, right? So if we do that, what are we up against? We've got I1 minus I2 plus I3 equals to 0. We've got minus 5I1 plus 4I3 is equal to 2. And finally, we've got 4I2 plus 4I3 equals to minus 2. Right? And what were we trying to solve for here? We're trying to find I1, right? That was the question. Do you guys know how to just solve for I1 if you want to? Did you know there's a formula? It's called Kramer's rule. And so I can write it down for you. I1. So this gives us the matrix 1, minus 1, 1, minus 5, 0, 4, 0. And it would be worth your time to figure out how to solve these on your calculator, right? I allow you to have a calculator in here. And this is one place where your calculator could really, really shine, is solving these systems of equations. Because I do expect you can do it and do it correctly on the test. And it doesn't matter to me too much if you use technology. Like, I'm not testing on whether or not you know how to do substitution, as I've been mostly doing it in class, right? Now, admittedly, you pretty much have to do the algebra for the, like the problem we did last class that took 25 minutes, that thing. I don't know how to do that with a calculator, I don't think. I think I have to do that with the kind of calculations we did, because it's got a mixture of calculus and algebra, But this, there are standard techniques. So the one thing you could do is just shove this thing. You could calculate the fastest way to do it in your calculator to get all the answers that your heart desires is to simply calculate the reduced to echelon form of this. So you put this matrix in your calculator, and what it will pop out is 1, 1, 1, and zeros. And the answer for I1, I2, and I3 over here will actually be the answers. That's the quickest way to find everything. Kramer's rule says you can calculate the determinant. All right? And this is kind of funny. It's a little bit, it's a weird thing, but here's how it goes. Kramer's rule says you take the variable you're interested in this case, the first one. You swap that column out, and you put 1, minus 5, and 0 there. everything else stays the same. The -1, the 1, the 0, the 4, the 4, and the 4, right? You guys already know how to calculate determinants because you've done cross products. And it's the same pattern, all right? So like down here, you got just the determinant of 1, -1, 1, -5, 0, 4, 0, 4, 4. All right?
Are you supposed to be replacing that column, the upper determinant with 0, 2, and -2?
Oh yeah, did I not do that? Oh man, I said it, but then I didn't do it. Or I don't know what I said. It's been so long. 0, but yeah, that was supposed to be this. Thank you. So that is supposed to be I1, right? Which we can calculate somewhat quickly here as 1 times 8 plus 8 plus 1 times 8 divided by 1 times -16 plus 1 times -20 plus 1 times -20, I think, if I haven't made a mistake, which would be surprising. That would be 24. I mean, I don't put a lot of stock in this answer, guys. What's that? -40, -56, I think. So allegedly, if I haven't made a mistake, which I'm, again, not super confident about, because this, you know, these require care, and I'm hurrying a little bit. So I get minus 0.4286, and that would be in amps. So allegedly, wait, 0.43? Wait, 0.43. Yes. So there you go. That's the answer. Of course, the book did not specify which way is positive, so the book has plus 0.43, but you know. Do you guys know about this RREF thing? Let me show you. It is in the Casio 115 ES. Like, you can do this in here. You can do these in here. It is better than you at calculating this. I mean, I know it because it's better than me for sure. Like, these are just fundamentally complicated. So if you go down to my websites that do the math for you, eventually down here. Oh, I went too far. Oops. Let's see here. Where did it go? This one here, number 3. And you go to transforming a matrix to, this is, I mean, you can just put the equations into Wolfram Alpha 2, of course, but you can't do that on the test. You also can't do this on the test, but you can do this on your calculator. If you have mine, at least. What were the numbers? 1, -1, what? 1, 0, -5, 0, 4. It's not hard to learn how to write this matrix down, guys. It's like it's pretty easy, really, what I'm doing. If you don't know what I'm doing, you're not far from knowing it. And so it takes 7 row operations, but this right here, that's actually what I got in my calculator, was 3/7 for I1. That is 3/7. Maybe you can even see it, I don't know. 24 divided by 56, factor an 8 out, right? So there's I1, there's I2, there's I3. So it gets all 3 of them at once, this method. Which is better than, Cramer's rule does require like more arithmetic, right? Anyway, I'll shut up. Have a good break, guys.